Hello students, welcome to ALPHORES e-learning channel. This is K. Nageshwarrao, your physics faculty. Today we are about to deal with session number 109, second year Neet. The chapter name is Magnetism and Matter. So in the previous chapter we have dealt with, in the previous sessions we have dealt with magnetic moment in case of bending of magnet, cutting of a magnet, and if you take magnets, different magnets in different orientations, the resultant magnetic moment. All these details we have discussed in the previous sessions. And in this session, I'll start with further discussion. So let us see what we can do. So before I start with the session, I'd like to quote one important point. Okay, see, students, in first year, you might have seen there is a lot of lot of similarity between translatory motion and rotatory motion. I mean, whatever physical quantities you see analogous physical quantities in case of rotational motion also. Whatever physical quantities you see in linear motion, analogous physical quantities you might have seen in rotational motion. For example, if you talk about mass in translatory motion, in rotatory motion you are going to talk about inertia. If you talk about force, you are going to talk about torque here. If you are talking about linear momentum, you will be talking about angular momentum here. Okay, if you are talking about a linear displacement, you will be talking about angular displacement. Whatever kinematic equations you are familiar with, all those kinematic equations can be written in case of rotational motion also, isn't it? So like that, there is a lot of relevance, similarities are there. Okay, so once you look at these two domains together, you feel very comfort in handling the data. Okay, if at all, if in one particular field, if you are not able to access a point, you can take the other field as a reference and you can access that point immediately. So like that, here also in second year we have one flexibility between two chapters. One is electrostatics and the other one is this magnetism and matter. And already I gave you a few points earlier in the previous sessions. I have quoted here and there whatever relevances are, whatever analogous terms are there between electrostatics and magnetostatics. So let us try to understand a bit more about this. So in electrostatics, if you are talking about charge Q, here pole strength M, isn't it? Here if you are talking about electric dipole moment P bar, here magnetic dipole moment M bar. This P bar is expressed as Q into 2L bar. This M bar is expressed as M into 2L bar, isn't it? So these are what two analogous terms that we have seen so far. And further, you can extend this discussion. If you are talking about Coulomb's law here in electrostatics, you can talk about Coulomb's law in magnetostatics also. Okay. So what is here Coulomb's law? Coulomb's law is F is equal to what? K Q1 Q2 by R square. Here this can be written as F is equal to K pole strength M1 M2 by R square. Okay, if you are talking about electric field strength E bar, you can talk about magnetic field strength here. I'll tell you about that. Okay, if you are talking about, in fact it is denoted with B bar, I'll discuss that thing today. If you are talking about electric flux here, pi E bar, you can talk about magnetic flux pi B bar. Here electric flux, how it is expressed? It is expressed as what? E bar dot A bar. We have seen this already, isn't it? And this E bar is expressed as force per unit charge, test charge. Similarly, here also B bar can be expressed as force per, in place of charge, what you are going to write? You are going to write pole strength. So like that, there is a lot of analogous between these two fields. If you are talking about tau in electrostatics, tau is expressed as P bar cross E bar, P is sin theta. Similarly, here also you can talk about tau. Okay. So like that, there is a lot of relevance between these two fields. Okay, I want you to understand this point so that you will be able to handle the data in both the fields very easily. Okay, so now our job is going to become simpler because we are very much familiar with all these terms or with all these concepts. So we can take advantage of this situation and we can try to understand all relevant situations in magnetostatics. Okay, so let us proceed with Coulomb's law for magnetic force. We'll start with that. Okay. Coulomb's law for magnetic force. For example, if you are having two isolated poles, M1 and M2, with the pole strengths M1 and M2. Let us say the separation between these two poles is R. So, according to Coulomb's law for magnetic force, how it can be written? F bar is equal to, or F bar is directly proportional to product of two pole strength. Like in the case of electrostatics, force of attraction or repulsion between two charges is directly proportional to their magnitude and inversely proportional to square of the distance of separation between them. So here also the force between two poles is directly proportional to product of their pole strengths and inversely proportional to separation between those two poles. And here if you introduce a constant of proportionality k, it can be written as k into m1 m2 by r square, where this k is, you can call this as magnetic force constant. Magnetic force constant. And from the experimental data, this k is identified as mu naught by 4 pi. I'll tell you what this is. And its value is 10 power minus 7 Weber per ampere per meter. Its value is 10 power minus 7. In the case of electrostatics, k is expressed as 1 by 4 pi epsilon naught, where epsilon naught is what? Permittivity of a free space. And here mu naught is permeability of free space. That is permittivity and this is permeability. So this mu naught is what? Permeability of free space. I told you why do we introduce such kind of things earlier in the previous sessions also. Remember students, whether you are talking about refractive index or you are talking about permittivity or you are talking about permeability, these things will give us an idea about how a medium can influence when these field lines are passing through them. For example, if you are dealing with a charge, there will be field all around the charge, and when that field is penetrating through a surface, that material definitely influences the field because it has got its own field. Inside of that, atoms are there, inside of the atom electrons are there, nucleus is there, positive charge, negative charge, all are present inside the material. So definitely when field lines are passing through the material, it gets influenced by those fields inside the surface, inside the material. And different materials will have different kinds of electronic environment inside the material, isn't it? So different materials will influence the field lines to different degrees. Okay, so that to identify this or to understand this, we have introduced such kind of physical quantities. Here mu naught is what? Permeability of free space. This deals with how a medium can influence the magnetic field lines when they are passing through it. Okay, epsilon naught is what? Or epsilon permittivity is it's something that deals with influence of the material on the electric field lines which are passing through it. Okay, so this mu naught is what? Permeability of a free space. Okay, so this F now it can be written as mu naught by 4 pi m1 m2 by r square. So that's how the magnetic force can be written. Okay, and here for problem solving purpose, you need to remember this. Mu naught by 4 pi value is how much? 10 power minus 7. Okay, if at all, if anywhere mu naught is present, that mu naught can be replaced with a 4 pi into 10 power minus 7. Okay, so this is what about Coulomb's law of magnetic force. It's very easy to remember because it is completely relevant to Coulomb's law of force in case of electrostatics, where we write F as 1 by 4 pi epsilon naught into q1 q2 by r square. Here mu naught by 4 pi into m1 m2 by r square, isn't it? So let us proceed with magnetic field induction, like electric field strength. Here also magnetic field strength is there. So let us talk about that. Magnetic field induction. Magnetic it is denoted with B. It is denoted with B, and it can be defined as, like the way we have defined electric field intensity, here also magnetic field induction can be defined in the same way. Electric field intensity, how it was defined? It was defined as force per unit charge at a point is nothing but electric field intensity at that point, isn't it? So similarly here also, for example, if you consider a magnetic pole, and somewhere here you have considered one point P which is at a distance equal to R, and if you place one let us say this pole strength is M1. I'll take it as M1. Let us say here another pole is placed whose strength is M. Okay, so magnetic field induction at this point can be expressed as force, magnetic force per unit pole strength. That's how it can be expressed. So this F bar, how this F bar can be written based on, just now we have seen the Coulomb's law in magnetostatics. This F bar can be written as mu naught by 4 pi M1, and this is what? M by R square by M. This and gets cancelled. Therefore, B bar, magnetic field induction at a point P because of a pole whose strength is M1 can be expressed as mu naught by 4 pi M1 by R square. Okay. So in case of electrostatics, the same equation E is expressed as 1 by 4 pi epsilon naught Q by R square. Okay, right? So like that you can talk about this one. So basically magnetic field induction is a vector quantity. Okay, for example, if you have considered North Pole, and at a point P, if you wanted to find out the direction of a magnetic field induction, its direction will be like this, along the direction of the field. We have already seen from the North Pole, the field lines will originate. Okay, so like the way, from plus Q, field lines will originate. No, similarly here also, analogous to that, field lines, they originate from the North Pole, and a magnetic field induction or field strength will be along the direction of field line. So in case of North Pole, the magnetic field induction is away from the pole, and in case of South Pole, if you take a South Pole like this, let us say there is a point P at a distance R. In case of South Pole, the field induction will be towards the pole. Like in case of negative charge, the field induction is towards the charge. Electric field strength is towards the charge. Here, field induction is towards the South Pole. Okay, and coming to its units of B bar. SI units, Weber per meter square, or Tesla. Weber per meter square or Tesla, or simply you can write this as capital T. Here you can write this as WEB pi n square. Simply like that you can write Webers per meter square or Tesla. And coming to CGS units, Gauss. It is expressed in terms of Gauss. 1 Gauss is equal to 10 power minus 4 Tesla. This conversion is also important for solving numerical problems. Sometimes we need to convert from Tesla to Gauss. 1 Tesla is equal to 10 power 4 Gauss. So 1 Gauss is equal to 10 power minus 4 Tesla. Okay, so these are few details connected with this magnetic field induction. If you want, with the help of this equation, you can write dimensional formula. So let us try that. Dimensional formula of B bar. So this B bar is expressed as a force per unit force strength, isn't it? So we know that force dimensional formula is m power 1, L power 1, T power minus 2, isn't it? What about dimensional formula of pole strength? Units of pole strength are ampere meter. Okay, so dimensional formula of pole strength is ampere length. So if it is further simplified, you will get m power 1, L gets cancelled, L power 0, T power minus 2, A power minus 1. So this is what the dimensional formula of magnetic field induction. So these are a few fundamental details connected with magnetic field induction. Further, we need these details to handle problems as well as to deal with further derivations. Okay, so all that you need to remember is magnetic field induction due to a pole at a distance r is expressed as mu naught by 4 pi into m1 by r square. Okay, so that's how it is expressed. So now let us proceed further with magnetic flux. In case of electric flux, it's defined as, just now I have shown you E bar dot A bar, right? Mathematically, that is how electric flux was written. So here, magnetic flux it is denoted with the pi subscript b. It is just an quite relevant to what electric flux. In case of electric flux, it was told to you that the number of field lines passing through a surface is called as flux through that surface. Similarly, here also the number of magnetic field lines passing through a surface is nothing but magnetic flux through that surface. The net value of number of field lines passing through a surface is nothing but magnetic flux through that surface. So mathematically it is expressed as relevant to that b bar dot a bar. In case of electrostatics, it was written as e bar dot a bar, right? So here it is b bar dot a bar. Scalar product, so scalar product yields a scalar, so this is magnetic flux is a scalar quantity, right? So where b bar is magnetic field direction, a bar is area vector. For example, if you take one surface, something like this, if a field lines are passing through this surface in this way, okay, and if you wanted to find out flux particularly through this area, imagine one normal to this surface. So along that normal, okay, you will be considering area vector. Okay, a small area, and to that you have to imagine a normal. Along the normal, area vector's direction exists. So this area vector a bar can be written as a into n cap. Very particularly, this is written as n cap because I want you to remember this point. Whenever we deal with area vector, it is always considered normal to the surface. And this one can be further written as BA cos theta. Magnetic flux. And where theta is angle between the field and what area vector. For example, here field direction is this one, right? So whatever this angle is there, that angle between b bar and a bar is called as theta. For example, if the surface is like this is the area vector, and magnetic field is also along the same direction, then the angle between those two things is how much? 0. So there will be maximum flux passing through the surface, because pi b, or whether it is maximum or minimum, it is decided by theta. If theta is 90 degree, for example, field is along this direction and the surface is horizontal, so this is the direction of area, this is the direction of b bar. Now what is the angle between these two? Angle between these two is 90 degree. So when you replace theta with 90 degree, what you will get? Cos 90 is 0. So flux passing through this surface will be 0. And whatever points I am quoting here, these points are quite analogous to what all the electric flux related points, isn't it? So, and what about the units of flux? Units. In SI system, the units are Webers. It is expressed in Webers. Okay. In CGS system, it is expressed in Maxwell. Okay. 1 Weber is equal to 10 power 8 Maxwell. This is the relation between Webers and Maxwell. Like the way we have a relation between Gauss and Tesla, here this is the relation. 1 Weber is equal to 10 power 8 Maxwell. Okay, or 1 Maxwell is equal to 10 power minus 8 Weber. Okay, so you just remember these points. Now let us talk about one more point. That point is quite relevant to whatever we have discussed earlier. Magnetic flux density. What is this? Let me talk about here itself. Magnetic flux density. Magnetic flux density is nothing but B bar only. This is expressed as, from this equation, it can be written as pi A by A, or the magnitude can be expressed as pi A by A, flux per unit area. Density, yeah, it's relevant. I'm talking about magnetic flux density, and flux is something that is connected with the surface, right? So how much of flux is present per unit area? That's nothing but magnetic flux density. Okay, and this is what we have already called it as magnetic field induction, and we have seen its units also, right? Webers per meter square or Tesla, or it can be measured in terms of what, in the units of Gauss. Okay, so whether you are talking about magnetic flux density or magnetic field induction or induction field strength, all these terms are relevant. Don't get confused with all these terms. They are not unique. They are same. Like they are not different. They are same. Okay, so this is what magnetic flux density, and this is nothing but magnetic field induction, or we can also call this as flux density. Okay, so these are a few important points connected with magnetic field. All that I have talked about is magnetic field and its influence. If there is a unit north pole, there will be field all around that. And if you place another pole of strength, some M or M naught, test test north pole, it experiences some force. We have seen how much force it experiences with the help of Coulomb's law. And at whatever point you are keeping that pole, there will be some field strength. And we have seen how much is that field strength, how to find out that field strength. Okay, and around this, whatever north pole you have considered, around this, if you imagine a surface, how many field lines are passing through that? If you are interested in that point, that can be studied under the category of magnetic flux density, magnetic flux. And if you wanted to find out through unit area, how many field lines are passing, okay, you can use this one, magnetic flux density. Okay, so this is how you can handle this data. And let us talk about uniform and non-uniform magnetic fields, because frequently we will be using these two terms in further sessions. See, uniform field in the sense, in whatever region that field exists, in that region at every point, the direction and magnitude of magnetic field induction should be same. If that is the situation, you can call that field as uniform magnetic field. For example, if this is how field lines are represented, equally spaced, okay, if you imagine one point here magnetic field, let us say V bar, and its direction is like this, okay, along the x-axis, let us assume like that, BA cap, okay, and if you imagine another point here also the direction and magnitude of field strength both will be same. If such a kind of scenario is existing at all points in this field, you can call that field as uniform magnetic field. And if this fails, like here, let us say there is one magnetic field and here another magnetic field, or both are two different magnitudes, or direction is different. Let us say here the direction is like this, here the direction is like this. If that is the situation, you call such kind of magnetic field as non-uniform magnetic field. For example, if you take a bar magnet, this is north pole, this is south pole. Okay, so here if you imagine a small area, small region, okay, in this region particularly, the field strength is going to be constant everywhere, okay, because they seem to be very equally spaced. I'm talking about considering a small region. But if you imagine such a kind of region here near the poles, the direction will be different. Near the poles in the sense, not very close to the pole. If you consider very close to the pole, it will be same. Direction will be inwards in case of south pole at all points, isn't it? If you imagine a region on the surface of the pole itself, where the field lines will be normally into the surface, isn't it? So nearly they will be normal into the surface. But here in this region, they are very much crowded and all are curved. Since all are curved, the direction won't be same. Direction of the field induction won't be same near the poles. So this you will have a kind of non-uniformity. And here you can imagine if you consider a very small region. In fact, Earth is a gigantic magnet. It's a big magnet. Okay, so in further sessions we will be talking about horizontal component of Earth magnetic field. Okay, so in a particular region, in a small region, you can find several such kind of small regions across the globe. You will have uniform magnetic field. Okay, but it's quite difficult, there will be several other fields involved because of various materials present in different regions of the Earth. The field will be, it exists randomly. Okay, so these are a few fundamental points connected with magnetic field induction. Okay, students. So with this, I will conclude the session, and in the next coming session, we'll deal with problems connected with this one, and we'll extend the discussion connected with magnetism and matter. Thank you, students.